Welcome to the mole. I'd like to make some introductory remarks first before we get right to the mole. Now, the mole is a very fundamental property in chemistry. In fact, it's one of the 7 fundamental physical quantities in science. 4 of them you're already quite familiar with, shown here: mass, length, time, and temperature. You're also familiar with their symbols, M, L, T, and capital T, as well as their standard units, the kilogram, meter, second, and Kelvin. You may not be quite as familiar with the Kelvin as a temperature yet, but with time you'll see that it's the most used temperature scale in science, and you'll be quite comfortable with it. To these 4, we now add a 5th, the amount of substance. Now, it's a bit of a mouthful. It's not as simple and clean as single words above, but it is, again, with practice, you'll be comfortable with this quantity called amount of substance. The symbol is N, and the unit is the mole. I don't know why N was chosen instead of M. I presume M had already been taken up by mass, perhaps, but N is the symbol. Now, I mentioned that there were 7. I'll just briefly mention the other 2. One of them is the ampere, which is a unit for measuring electrical current, shown here. And the last one is the candela, CD, which is a unit to measure luminous intensity, otherwise known as brightness. And here we have Kelvin for temperature, mass, length, and the amount of substance, mole, and time in seconds. So that takes care of that. When we now hear the word mole, it will likely bring up various images. The most common one is this furry little animal with very small eyes and a large claws, good for digging. Moles live mostly underground. Some of them are hairless, but there you go. Here's the mole. There's also the mole on our skin, on face, arms, various parts of our body, a little brown spot. Sometimes there's many of them. And then the perfect spy for Moscow. Here is a mole, famous in TV and movies. Now, there's a final sense of mole which very few people are aware of. I was surprised when I found out about it, which is a large concrete barrier in the water. It serves as a breakwater so that, for example, if there's rough weather, this breakwater will break up waves before they come to the shore and do a lot of damage. It can also be a series of stones. Wood can be put on top of it to serve as a pier, except in a pier, water can go underneath a pier, but in a mole, the water is stopped. It's interesting to see how one small word like the mole can have 5 such completely different meanings. Now, this video is about half an hour in length, and that might be a bit much for some of you. The mole is being discussed in 3 different senses, so you might want to do it in 3 different sittings. That's up to you. In any event, the reason I did it this way was that if in the future you need to come back and see something about the mole, you'll know that everything is in one location. All right, so having said that, we'll go on to the mole. I hope you find it interesting, informative, and useful for your classes. As mentioned above, the amount of substance is measured in units called mole. Now, let me just take a moment to discuss its Latin origins. Molus from Latin means matter, and therefore mole refers to a quantity of matter. By the way, the word molecule is a diminutive form of mole. In other words, a small piece of matter. You may know some words ending in ule that are diminutives in English. For example, minuscule, a small amount, even smaller than mini. Capsule, the diminutive of the Latin capsum, which means box, so capsule must be a small box. And granule, a small grain. There are 3 senses of the mole. First, mole as number, then mole as mass, and then mole as volume, and that applies to gases only. I'll do each of these in turn, starting with mole as number. 1 mole of any substance contains 6.02 times 10 to the 23 particles. Now this is a large number and it has its own name. There are some words in English that stand for certain numbers that you already know. For example, what name do we give to two things? You would probably say pair, or perhaps a couple. For 12 things, the name would be dozen. You may even know 144 things. The name for that is gross. And in the paper industry, when they package 500 sheets together of 8.5 by 11 paper, that package is known as a ream. And there are others as well. But to this list we simply add mole with its number. Now this number also has another name called Avogadro's number. Avogadro was an Italian physicist, but he actually did not calculate this number and did not have anything directly to do with this number. It was another French chemist who honored his name with this number about 50 years after he died. I'll deal with this a little bit later on in the video. The number has its own symbol, which is capital N, or N subscript A for Avogadro. Either one is fine. Now let's look at the word particles again, because it can be one of three things. It can be an atom, so for example elements like sodium, carbon, iron, they're all individual atoms. They're held together in clumps by electrical forces. We have molecules like oxygen, water, and ammonia. They are discrete little compounds that have their own boundaries, and they're held together within by covalent bonds. We then have ionic particles. They don't have boundaries. You can grow large crystals of them, but they are characterized by ionic bonds, such as in sodium chloride or copper sulfate. So when you're answering a question, you need to determine what kind of particle we're talking about, and that will either be pretty clear from the formulas that you're given or from the actual word that's in the question. Now let me ask, how many dozen are there in 62,500 things? In order to answer this, you would divide by what a dozen stands for, which is 12. In the same way, if we want to know the amount of substance in moles, we'll take the number of particles that we're given and divide by Avogadro's number. We use the usual symbols, small n for amount of substance. Now, number of particles is not an official designation, but it is the most common one that you'll see anywhere in textbooks, so we'll stick with that. And Avogadro's number is uppercase N, and we just join them with the equal sign. And here we have our first relationship between amount of substance and number of particles. So let's look at one typical question. Always make sure you look carefully at the words and the numbers in a question so that you can relate them to the letters that are represented by them. For example, look at the word amount. Now that should suggest N, so you're looking for N there. And look at the number. That number should reflect then number of particles P. So now you know that you're looking for N. We can use the formula as is, and we'll simply write it down here. Put in the numbers. Notice how the word atoms cancel out, and the final unit, which should be moles, is actually moles. Here's our answer, 4.3 times 10 to the minus 3 moles of lead. So how big is Avogadro's number? Now, there have been many comparisons, very interesting ones, and one that I like is called the green pea analogy. It was devised by a couple of American chemists back in the 1980s and has been updated now for Canadian audiences. And it goes like this. Let's start with 100 peas. And we write the number 100 as 10 squared, and we could have an image like this of 100 peas. Let's go to a million now, 10 to the 6th, a larger number, and these peas would fill a household refrigerator. Let's now go to a billion, 10 to the 9th, and the peas, those number of peas would fill a whole house from cellar to attic. We can now go to a billion, 10 to the 12th, and that number of peas would fill 1,000 houses. We go to a still larger number, 10 to the 15th, and this would fill all the buildings in a city such as Calgary or Edmonton. Now, for 10 to the 18th, we need a larger measure. Let's look at the province of Alberta. Now, let's suppose that there's a blizzard over Alberta, but instead of snowing snow, it snows peas. Alberta is covered with a blanket of peas about 1 meter deep, all the way from Saskatchewan out to British Columbia, and all the way from the United States to the Northwest Territories. This blanket of peas drifts over the road and banks up against the sides of the houses and covers all the fields and forests. Think of flying across the province with a blanket of peas extending as far as you can see. This gives you an idea of the next number. There will be in this blanket of peas about a quintillion, 10 to the 18th. Now we go to 10 to the 21st. Let's imagine this blizzard of peas falls over the entire land of North America, Africa, South America, in other words, all the continents of the world. They're covered with peas, and this gives a number 10 to the 21st, which is a sextillion. Let's imagine now that all the oceans are frozen, and the total surface of the earth is covered with peas that go 1 meter deep. Let's then go out into our galaxy, collect 250 planets all the size of the earth, cover each of them with a blanket of peas 1 meter deep. Then you will have 1 mole of peas. That's quite the number. Now the authors wanted to go one step further, 10 to the 27th, which is a cotillion, and they say that if you collect 250,000 Earth-sized planets, cover all of them with peas 1 meter deep, you will then have a number corresponding to the number of atoms in your body. This number and that comparison pretty well boggles my mind. Let's now look at the mole as mass. The molar mass of an element or a compound is its atomic mass or formula mass expressed in grams. Atomic mass would refer to elements, and formula mass refers to compounds. Now let me just insert a brief historical moment here. The mole as a unit in chemistry was first introduced by a German chemist, Wilhelm Ostwald, in about 1897. He defined the mole as the molecular mass in grams, which is essentially the same today, except we use a more general term, molar mass, although molecular mass is also sometimes used. Now, let's consider a example here. We'll look at carbon. From the periodic table, its atomic mass is 12.01. It's 12.011, but I'll just take it to 2 decimal places for our purposes. If you weigh out 12.01 grams, then that will be 1 mole as expressed up here. In other words, we can say the molar mass of carbon is 12.01 grams. Another way of saying the same thing is 1 mole of carbon weighs 12.01 grams. So these are equivalent statements. They mean the same thing. Let's look at some examples from the periodic table. Let's look at iron here. The atomic mass of iron is 55.845. Now, this atomic mass is a relative mass. That is, this is how much iron weighs compared to a selected element as the standard, and that element is the isotope carbon-12. In fact, all of these atomic masses are the masses of these elements compared to the mass of that isotope carbon with the mass of 12.00. That's defined to be exact. If we now weigh out 55.845 grams of iron, then we will have 1 mole of iron. Similarly, if we weigh out 106.42 grams of palladium, we will have 1 mole of palladium. We can say that the molar mass of palladium is 106.42 grams. Okay, two different ways of saying the same thing. By the way, these two elements, osmium and iridium, are interesting that they have the highest density of any element. So these atomic masses, 190, 192 in grams, would be the molar masses of osmium and iridium. You also know from the previous section that if this is a mole of a particular element, you know how many atoms there are. So there are Avogadro's number, that is 6.02 times 10 to the 23rd iridium atoms in 192 grams of it. In all these cases, the atomic mass of all of these elements in grams all contain the same number of atoms in these masses in grams. Let's consider now the molar mass of some compounds. I've left a space here and here for you to fill in or to think about. In order to determine the molar mass of water, we have to know its formula. Well, that's simple enough. That's H2O. All we do is add up the atomic masses to get the molar mass, so 2 hydrogens at 1 each, plus oxygen, which is 16, adds up to 18. So therefore, 18 grams would be the molar mass of water. Let's look at nitrogen. What is the formula? Be careful not just think that it's N. N is the symbol of nitrogen, but it's not its formula. There are gases like nitrogen, oxygen, hydrogen, chlorine, which in nature exist as diatomic molecules, and therefore the correct formula would be N2. So therefore we take 2 of these times 14, which is the mass of 1 nitrogen. That gives us 28 grams for a mole of nitrogen gas. Ammonia, formula NH3. We simply add up 14 plus 3 hydrogens at 1 each is 17. So the molar mass of ammonia is therefore 17 grams. Now we can develop the relationship between amount of substance and mass as we did above with number. You take the mass of a substance given in the question, divide by its molar mass, and that gives us the amount of substance in moles. N for amount of substance, small m for the mass of the substance, and capital M for the molar mass. So here are the definitions for N. M, this is your sample mass, sometimes it's called, and molar mass. Now, N and M are variable. They can change, but capital M molar mass is fixed, and that's determined by the formula of that substance. Let's look at 2 typical questions. Find the amount of substance in 200 grams of carbon dioxide. Again, pay attention to the words and numbers and relate them to the letters. If we look at the word amount, then that should indicate to you that we're talking about N. When we see 200 grams, that's an amount, that's a mass, that should lead us to small m. And from the formula, that allows us to calculate the molar mass of carbon dioxide. Since we're trying to find N here, we can just take the formula as it is, write it down, put in our numbers, notice how the grams cancel out, and our answer is in moles as it should be, 4.5 moles. In other words, 200 grams of carbon dioxide is the same as 4.5 moles of carbon dioxide. One more question. Find the mass of 2 moles of HNO3. Again, we see the word mass. That should lead us to connect it with little m. We see moles, 2 moles, and that word should connect us to N. And from the formula, again, we can determine the molar mass. This time we have to find little m, so we're going to manipulate the equation around to get m by itself, and then turn it around so that the variable we're seeking is on the left side. That's the normal way of showing these solutions. put in our numbers. 63 grams per mole is the molar mass of nitric acid. And here's our answer. 126 mass is 126 grams. Really should write of HNO3 to complete it. Now let's look at this picture. This is showing water in a test tube. This is 18 grams of water, and you know 18 grams up here is 1 mole. Now let me remind you previously where we talked about a mole of peas. It would cover the entire Earth plus 250 planets the size of Earth 1 meter deep. Imagine taking all those peas and shrinking them down small enough so they would all fit in this little volume. That should give you some idea of the incredibly small size of molecules. We now come to the third and final sense of mole as volume, and this applies to gases only. 1 mole of any gas contains 6.02 times 10 to the 23 molecules. Let's come back now to Avogadro. Here's the only picture you ever see of him. And back in 1811, he proposed that if you took any gas, then the number of molecules in a given volume would be the same, provided the temperature and pressure were constant. So here we have hydrogen, nitrogen, oxygen. We make sure that the temperatures are all the same, the pressure inside the balloon is all the same, and in such a case, and the volumes are all the same, and in such a case the number of molecules of any gas will be the same. Now he wasn't able to determine what that number was, but his hypothesis was proven to be correct. It began to be accepted about 50 years after he made this hypothesis, after he was dead. And about 100 years later, a French chemist, Jean Perrin, was the first to actually give some determination of the value of N, 6.8 times 10 to the 23. And to honor Avogadro, Perrin decided to call this number Avogadro's number. Now it should be noted that Avogadro's number is a bit of a misnomer because it never was his number, and in fact it should be called the Avogadro constant, especially since in 1971 the International System of Units accepted the mole as an amount of substance as a fundamental unit, and therefore the Avogadro constant has a unit now which is reciprocal moles, in other words 1 over mole. Finally, this number is an experimental determination. There are various different methods that can be used to try and determine it. There's even a high school experiment that can be used to get an approximation for it, but this has been rounded off to 2 decimals. The most accurate number now has at least 8 decimals, but we usually just round it off to 2. Now coming back to these balloons and their volume, if you put 1 mole of any gas into a volume which has the same temperature and pressure, what actually is that volume? So that has been again experimentally determined to be 22.4 liters under standard conditions. Now let's just spend a moment on understanding standard conditions. There are 2 of them. The first one is temperature, 0 degrees Celsius. So anything in chemistry to do with gas laws, that is the standard temperature. In other parts of chemistry, the standard temperature may be 25, but here it's 0. And then there is standard pressure. So 1 atmosphere is a standard pressure, but that's equivalent in kilopascals to 101.3, which is equivalent in millimeters of mercury to 760. So these together, standard temperature and pressure, are referred to as STP. So we end up with the molar volume of any gas at STP as being 22.4 liters. If you change the temperature, then this volume is going to be a different number. So now we can again relate the amount of substance, in this case the amount of gas, to volumes. As we have done before, the gas volume or sample volume divided by the molar volume can be represented by N equals V, small v, over capital V, sometimes subscript M to denote molar volume. Again, the V and N are variable, but the capital V is a constant. Now, let's note what we have seen. We've seen that N initially was amount of substance related to number of particles divided by the Avogadro constant. We've seen N was also equal to mass over molar mass, and now we bring this ratio down and volume over molar volume. So because they're all equal to N and equal to each other, any combination of two equations may be used to solve problems in one step. Now let me explain. We can clearly set N equal to this ratio, or to this ratio, or to this ratio. But in addition, we can also take this ratio and combine it with this one to solve for either mass or number of particles. N and M always remain constant. Or we can take this ratio and set it equal to this ratio if we have to solve for either small volume or number of particles. And finally, we can take these two ratios and set them equal to each other and solve either for mass or for volume. I have three examples here. Let's see how they work. What amount of ammonia is present in 2.24 liters at STP? Alright, so we can see we're going to link amount again to N. This volume, 2.24 liters. Now don't be caught off guard by thinking this is 22.4. It's a little trick. 2.24 is going to be your sample volume. So that's right here. And then molar volume is a constant. So therefore we're looking at N equals V over V. That's a straightforward one. So we write it here, put in our numbers, see how the units cancel out, give us moles. I've added two zeros here to give three significant digits in recognition of the fact that there are three significant digits here in the problem. Problem 2, how many molecules are there in 0.56 liters? So let's analyze this question. When you see many molecules, how many molecules, that should suggest to you number. So we're looking at P here. 0.56 liters, this is a volume, liters is a volume, so we're looking at this ratio. So therefore we can take this ratio and this ratio, combine them together. We're trying to find P. So if I write it here, you see I've taken the N and brought it over here to this ratio, and this is our final expression. We can now put in our numbers. Notice this is molecules, because you can see the formula here. This is a molecular substance, plus the word molecules is in the question. So that's why we choose molecules here, and it's per mole. The Avogadro constant is always per mole. And now liters over liters, everything cancels out to give us number of particles, which is molecules in this case. The final problem, what is the mass of 112 milliliters of methane? Okay, so mass suggests little m here, so we're going to use this ratio. Milliliters is volume, so we're going to be using this ratio. So these two ratios will be put together. And since we're trying to find mass here, this large M will be cross-multiplied over here to give us this expression. Now, in order to get molar mass, we're going to need to know the formula, so that's why it's shown up here. And now we can fill in our numbers. 16 is the molar mass of methane. Now notice here, we have to make a change. This is milliliters, but the molar volume up here is liters. So you have two options. You can either multiply 22.4 by 1,000 to get milliliters to agree with this unit, or we can divide this number by 1,000 to get liters. So I've decided to divide by 1,000 just to have smaller numbers here. So we have liters and liters. Everything works out now. We get our mass in grams. Again, I've added two more zeros to give three significant digits in our answer to agree with the three significant digits in the question. Now that takes care of the three senses of the mole. And I have one final extension here, interesting extension, involving the density of a gas. The density of any gas at STP is easily determined without having to look it up. For example, how would you determine the density of carbon dioxide at standard temperature and pressure? We know that density is mass over volume in general. When it comes for a gas, let's choose the density of the gas to be its molar mass over its molar volume. We know the molar mass of carbon dioxide from the formula. We know what the molar volume is at STP. So if we just put these numbers in, 44 is the molar mass of carbon dioxide, we get 1.96 grams per liter. Well, let me go back up here for a moment. You have learned in this video what molar mass is. You know what molar volume is. And using these simple but powerful concepts, you're now able to calculate the density of any gas without having to look it up or receive any other information. All you have to know is the formula. You would never have been able to do this before. So I think that's a pretty cool application of the mole concept. I'll leave you with one simple challenge. Figure out the density of xenon gas here at STP and decide whether if you put it into a balloon it would float or sink. You have to know that the density of air is about 1.28 grams per liter. After you've done that, come back to this video and watch a short clip of somebody who's actually put xenon in a balloon.
We've got a sample of xenon. Now xenon's one of the inert gases, but it's one of the inert gases that's right the way down the bottom of the period. So it's really, really dense. So we've done an experiment here and we filled this balloon with xenon. Now xenon's very expensive. So we're going to do this experiment and we're going to see if it sinks. And I think you'll agree that it does sink quite quickly. Now this is one that we've just blown up with air. So let's see if we can compare the rates at which these two balloons will sink so we can look at the comparative densities. Ready?